So in this video, I want to give a number of definitions that relate to travelling between the vertices in a given graph. And the example I've chosen to illustrate these definitions is this graph here with 6 vertices. Each vertex has degree 4, so it's a regular graph. Vertex degrees are all equal. And therefore there are 24, 6 fours, 24 divided by 2, that's 12 edges. So this graph has 6 vertices and 12 edges. Actually, it's isomorphic to the graph formed by the vertices and edges of an octahedron, if you can imagine that. You can see a number of triangles here, but they're also sort of triangles with curved edges. Remember, when we talk about graphs, we're only interested in the connectivity, whether or not 2 vertices are joined together. So, in any case, let me start with some definitions that help one understand the properties of graphs. So, the initial definition is that of a walk. So, these are technical terms, but most of the terminology is standard, but not always universal. And I'm going to try and stick to these terms I'm using. A walk is just a means of travelling from one vertex to another in any way you want, but obviously you have to go along edges. So to describe the edges you're taking for going from one vertex to another, you give the succession of vertices. So one says that 2 vertices are adjacent if they're joined by an edge. So in this example, we start with the edge A to B. We're starting at A and we're going to B, to D, sorry. So the first edge here is A to D. And if we look at the graph, there's only one edge that joins A directly to D. We have to look to join A directly to D, and that's going along that edge there. So that's what we do. And then we go to B, so we're going from D to B, and then we're going back to D. So in a walk, you're allowed to do that. You can go along an edge and go backwards. We're going back to D, then we're going to E, and then we're going to finish off at F. So this sequence here, this sequence of adjacent vertices defines the walk, or the trip, which I've illustrated on the left. And if we want to emphasize that we're starting at A, then if you want to put an arrow on it. So that's an example of a walk. And we can use this sort of very weak notion to discuss the concept of a graph being connected. So one says that a graph is connected if one can get from any vertex to any other. And it's an obvious notion. If you see the graph pictorially, it's obvious whether or not it's connected. It's obvious in this case I can travel from any vertex to any other by a sequence of edges. So this graph, this particular graph, is connected. Okay, but the point I want to make is that sometimes graphs are not given by pictures. If you want to load a graph on a computer, you've got to do it in a more combinatorial way, or by somehow describing the graph data. So typically this is done with either a matrix, and we'll talk about this later on, or a table. Can be done with what's called an adjacency table. Here's a small adjacency table that describes a graph. So this is to be interpreted as meaning that for example, if you look at this graph, again has 6 vertices, which are listed vertically. You can also list them horizontally. And you put next to them the vertices which are adjacent to that given vertex. So this table tells you you've got a vertex A. We can try and reconstruct the diagram from the table, and it's adjacent to vertices B and C. So we add edges, one going to B and one going to C. That takes care of the first row. And then B is adjacent to A, C, and E. So there must be, B is adjacent to C first of all, so we add an edge there, and there's another vertex E which it's adjacent to. And then C is also adjacent to E. It has to be adjacent to A and B, of course, so there's another edge there. And then we have another vertex not previously mentioned called D, and that's adjacent to F. So another vertex F. And now the picture's more or less finished because obviously E is adjacent to B and C, and F has to be adjacent to D. And that's it. There are no more edges. So although it wasn't completely obvious when you just look at this table for the first time, after doing a bit of work, you can see that this particular graph actually has two components. It's not connected. You can't travel from B to D, say. It's an example, it's a subgraph of the graph we saw previously, in which I've taken the same 6 vertices, but I've removed some edges, so it becomes disconnected. Okay, so that's the example, that's the notion of being connected or not being connected. Now, if you want to make this more rigorously mathematically, you can define an equivalence relation on the set of vertices of a graph by saying that 2 vertices are equivalent if you can walk from one to the other. If there's a walk, as I defined earlier, from that vertex U, say, to the other vertex V. But to make this into equivalence relation, you've also got to allow a walk that does nothing. You just stay at a vertex U and do nothing. So you can walk from U to U, if you like, trivially. And that gives an equivalence relation. For example, if you can walk from U to V and you can walk from V to W, you can certainly walk from U to W by just combining those walks. That's the transitivity property. So we have an equivalence relation. Whenever you have an equivalence relation, it partitions the set into disjoint subsets, and those disjoint subsets of vertices define what are called the components. I should have said, they define the components of the graph. So in this example, we have 2 subsets, 2 equivalence classes, one defined by the 4 vertices A, B, C, E, and the other subset defined by the vertices D together with F. So we have 2 equivalence classes, 2 components. And the other thing that I want to mention here as a warning is that sometimes if you have theorems or propositions about graphs, they will require that the graph be connected, particularly results about counting numbers of vertices or whatever. So be very careful when you look at a result and you're asked whether it's true or false. Does it say that the graph has to be connected? Because that result may be false if the graph may be obviously false if the graph is not connected. So be on the lookout for that. Okay. Now we come to a more restricted type of walk. It's called a trail. So in the sense of graph theory, a trail is simply a walk in which you're not allowed, as we did before, to go along the same edge twice. So you're not allowed to repeat an edge. Okay, that's a trail. Okay, so let me give you an example of a trail in this case. We can't use the previous example. So, for example, if you start with A and you go to B, and then you go to C, and then you go to E, and then you go to B, you're allowed to go back to the same vertex, provided you don't repeat an edge. And then we go to D, and then it says DF. Well, the only way of getting straight from D to F is to go along this curved edge there. Okay, so that's a trail. If you want to know where it started and where it finished, you put the arrow there. It went from A, started at A, and it finished at A. That's a trail because no edge is repeated. And here's, before I read out the famous definition, let me give you a longer trail, an example of a longer trail. And this trail will pass through every vertex. And it starts as it did before. This part of the trail is the same as before. So that means we went from A to B to E, to C, B to C to E. What was it? To B, back to B, then to D, and then to F. That's what we did before. But then the trail goes on, F to A. There's only one edge joining F directly to A. And then to D. That's that way. And then we go from D to E. So sort of going underneath here, we can visit the same vertex twice as long as I don't repeat an edge. And then we go from E obviously to F. Then we're going to C. And then we're going back to A. Okay, so this is a closed trail because we started at A, and I think it's clear if I just put a single arrow what's happening. It went all the way around and we finished at A. We finished finally at A again. Okay, so notice that I didn't repeat any edge. I repeated vertices. I started and finished at A. I repeated vertex B. I repeated C, E, D, F. But I didn't repeat any edge. Okay, and when you have such a trail, the graph is called Eulerian. It was Euler who studied the existence of such trails. Famous problem of the 7 bridges of the city that's now called Kaliningrad. And if you have a closed trail that covers every edge, the graph is called Eulerian. Now, the key observation about the existence of such an Eulerian trail is that it can only exist if every vertex has even degree. Okay, in this case, that's true. But if, for example, in this example, supposing that we were to eliminate this edge here, then we couldn't find a closed Eulerian trail, because we could, if we started at A, we could come back to A maybe going like that, but we can never come back finally to A because A has degree 3. We get stuck at some point. If you have degree 3, you can come in and come out of a vertex, but then you're stuck the next time. You've got to cover this edge. That's part of the definition of an Eulerian trail. You've got to cover this edge, and then what you do when you get to F, you can't get out again, so you're stuck. So for that obvious reason, all the vertices have to have even degree if the graph is to be Eulerian. If there exists a closed trail which covers every edge. Now, the interesting thing is that necessary condition of having even degrees is also sufficient. This is essentially Eulers' theorem, that a graph is Eulerian, there is a closed trail, if all the vertices have even degree. Okay, and it's not too hard to understand why that's true. I'm not going to show it in the picture, but essentially you can start by doing some closed trail that may not cover every edge, and if that doesn't cover every edge, you find out where you can put in another little trail, little diversion that covers more edges, and you keep adding such closed trails together, and eventually you'll get an Eulerian trail. And that's the basis of something called Herholtz's algorithm, which is explained in the notes. It's really quite straightforward, and that will explain why this theorem is true. If all the vertices have even degree, it is possible to find a closed. There may be many choices, but there will exist a closed trail that covers all the edges. So that's Euler's theorem. So just to emphasize here, the if is the difficult part. Only if is what I mentioned earlier. It's a necessary condition. There's another algorithm to find an Eulerian trail. It's called Fleury's algorithm, and that's described in the notes, and I think it's fairly straightforward, although there's another optional video if you want to look about that, see more about that. I ought to mention another definition that goes back to my picture in which I removed one edge. So you see, if we remove this edge here, the graph is what's called SemiEulerian. because although there isn't a trail that's closed and covers every edge, we can still cover every edge, provided we have two vertices of odd degree. So we've got to start at one of them and finish at the other. Otherwise we'll get stuck. So we can start at A, and we can still do more or less what we did before. Let's see if I can do this. So I want to start at A, I go around here. Here I have to go out. Here I can go to E, then I can go to F, then I can go, I've still got to cover, I can do those two, then I can go all the way around, I guess, and then I finish at F. So I haven't gone over any edge more than once, but I had to start at A and finish at F. So that would be called a semi-Eulerian trail, and that's possible, it's easy to see, that's going to be possible if and only if there are at most two vertices with odd degree, because you have to start at one of them and finish at the other. You can never have one vertex of odd degree, because the sum of the degrees of the vertices has to be an even number, because it's twice the number of edges. Okay, let's move on in our definitions, and now we come towards the end. Imposing even more restriction, I want to define something called a path, and a path is simply a trail which doesn't repeat any vertex this time. Okay, so here's an example. It is allowed to start and finish at the same vertex, but it can't, other than that, it can't repeat a vertex. So example, A, start at A, go to B, go to C, go to E, go to, we can't go back to B, we're not allowed to do that. So E to D is allowed, and then E to D to F. So that is, in this case, that's an example of a path, because no vertex is repeated. It's a path from A to F. And our path can be closed, as I mentioned, and if it's closed, it's called a cycle. So a cycle, let's see, the first example here is B to C to E to B. That's a cycle. Now, to be honest, well, this is called a three cycle. But when you talk about a three cycle, you don't really need to know where it started and where it finished. So I'm not going to put any arrows on or tell you where it started. This green, this selection of these three edges in this particular graph, it's what's called a subgraph, but it's a three cycle because it represents a closed path. Another three cycle would be simply to start at A, go to D along the circle, come back to A. Again, I'm not going to tell you where I started, or I'm not going to put an arrow on, it doesn't really matter. That sort of rough circle is an example. I've really just chosen these three black edges around the outside. That is another example of a three cycle in this particular graph. Okay, now since we're talking about simple graphs here, or at least this example is simple, there are no loops and there are no multiple edges. So if you have a cycle, it must contain at least three edges. It can't go to a vertex and go back because there are no multiple edges. So any cycle has at least three edges in a simple graph. This particular graph actually has 8 three cycles. Why is that? Well, it's these triangles here, they define 4 three cycles. Then there are 3 triangles around the outside, one with a curved edge, they define another 3 cycles, and then there's the one all the way around the outside, which I drew. That's the 8th one. And that corresponds to the faces actually of the octahedron, which I mentioned. Okay, now here's perhaps a more important closed path. It's an example of a 6 cycle I'm going to draw now. So this starts at A and it goes to B, and then it goes to C, E, D, I guess as before, and then it goes to F, and then it continues and goes back to A. Okay, so again, I'm not going to put an arrow on this. I'm just going to close it up and say that is a 6 cycle. It's 6 because it has 6 edges. 1, 2, 3. I shouldn't put those markers on. 1, 2, 3, 4, 5, 6. It has to have 6 edges because it covers all 6 vertices. Okay, and the question is, given a graph, can we find a cycle like that? So a cycle means it can't repeat a vertex except it comes back to where it started. Can we find such a cycle that covers every vertex of the graph? And if we can, the graph is called Hamiltonian. So this graph is Hamiltonian because we have a cycle that passes through every vertex. Now you can understand the problem like this. You see, given a graph, you can ask how many, does it have a 3 cycle? If so, how many are there? Does it have a 4 cycle? And so on. That is useful to understand if 2 graphs are isomorphic, because if 2 graphs are isomorphic, they have to have the same number of 3 cycles, 4 cycles, and so on. But the question is, if it has n vertices, can you find a cycle with n edges? You can't have more than n edges because then you'd repeat a vertex and it wouldn't be a cycle. But the question is, if it has n edges, can you find a cycle with that goes through all the vertices? So it has n edges. The cycle has n edges. So if the graph has n vertices, can you find a cycle with n edges? That's what I meant to say. And if you can, the graph is called Hamiltonian. And it can be quite a difficult problem, even with some quite simple graphs drawn by hand, to find such a Hamiltonian cycle, a cycle that goes through every vertex. Okay, so that's the problem of the Hamiltonian problem. You can read a bit about that in section 4.4 of the notes, although the important thing is just to know the definition and be able to recognize whether a number of fairly easy graphs are Hamiltonian or not. And there's no, unlike being Eulerian, there's no systematic way of knowing. It's not a matter of looking at the vertex degrees. It's a hard problem. One can't, sometimes there are conditions satisfied that tell you that the graph is Hamiltonian, but there's no sort of if and only if test. Let me just finish with a summary. So we started with the notion of a walk, and then we slowly made this more restrictive. So a trail means a walk where you're not allowed to repeat an edge. A path means a trail in which you're not allowed to repeat a vertex. Of course, if you repeat an edge, you must repeat a vertex. So a path, you're not allowed to repeat an edge or a vertex. And a cycle is a closed path. And just one exercise to finish with. If you have 2 distinct vertices in a graph and you can walk from one to the other, to find the equivalence relation I mentioned, if you can do that, walk means just any sort of meander from one to the other, you can actually find a path from one to the other. That means you're not repeating any vertex in the middle. And it's fairly easy that if you've got a walk, you can just remove edges if necessary to convert that walk into a more efficient path. Okay, I'll stop there.